All right, so in this chapter, we'll study Newton's laws of motion. Okay. Now, the first four chapters, we were just describing motion, and that subject was called kinematics. And when somebody asks you to describe a motion, what is it that they're asking you?
How is this object moving? Not what are the forces being applied to it?
Yeah, but we are good at math, so how do we want the description to be?
The net forces?
You want the position as a function of time. Okay, so this is what you were asking for. You were asking for those three functions. Yeah? And then from that, you could calculate the velocity. The velocity was dr by dt. And then the acceleration was dv by dt. Okay. You never asked what causes acceleration. Yeah. You were just interested in describing the motion. Now you learn what causes motion. What causes motion? Forces cause motion. Okay, and that's Newton's second law. Okay. So if the acceleration is changing with time, then the force you applied is changing with time. So for instance, you can think of, you're driving your car and you're pumping the gas or whatever, or a rocket is flying and the burn rate is changing. Okay? So if the forces cause acceleration. Okay, what if this guy is zero? What is the acceleration? I'm sorry? Zero. And if acceleration is zero, what does that mean?
There's no force acting on this object?
Right. No. What is it at rest? Is it moving?
Its velocity is constant.
Its velocity is constant. Okay. And this is Newton's first law. This is Newton's second law. Okay, so the first law really is a special case of the second law. I'm sorry? Okay. All right, you guys understand? All right. So let's look at Newton's laws. Okay. Isaac Newton, 375 years ago. All right. He came up with the laws of motion, published Philosophiae Naturalis Principia Mathematica. There he proposed scientific laws that are still used today. He discovered the law of gravity, he invented calculus, and made contributions to the theory of light and color. Okay? He was a smart fellow. Okay, so his first law of motion says, when no net force acts on the object. So net force just means if there are several forces acting on it, the net force is the sum of those forces. Okay? So if the net force acting on the object is zero, if the sum of all the forces acting on the object is zero, then its acceleration is zero and velocity is constant. Okay, so like we said, it's really a special case of Newton's second law. Okay? And here is Newton's second law. Okay? If you have a non-zero net force acting on an object, then the object accelerates. Okay? And its acceleration is force divided by its mass. So you can apply the same force to different objects. The heavier object will have a smaller acceleration. How many equations is this? sorry?
One?
One. Okay, it's three equations. When two vectors are equal to each other, when the x component of this is equal to the x component of that, y component of to the y component of that. Okay? So the x component of the force gives rise to the x component of the acceleration. All right, so what this is telling you is you can apply a force in the y direction that would not affect the x component of the motion. Okay? So the x component of the force gives rise to an acceleration in that direction and so on. Okay? So here are several objects. So here, if this is the x direction, all the forces are in the x direction, this will accelerate in the x direction. Which direction will this accelerate in?
To the right?
Yeah, so in the x direction. How about this guy? You'll have an x component to the acceleration and y component to the acceleration. So the net acceleration will be somewhere in that direction. How about this guy? He'll have an acceleration in this direction, an acceleration in this direction, which has both an x and y component. Anyway, the net acceleration will be somewhere in that direction. Okay? Okay, Newton's third law says the following. If an object applies a force on another object, this object will apply an equal and opposite force on that object. Okay, so what Newton is saying is all forces come in pairs. Whenever two objects interact, so for instance, if the Earth is pulling the moon with a force, I'm just going to make up some numbers. Actually, let's make more realistic numbers. So let's say your weight is 160 pounds. What does that mean?
It means at the Earth's surface, your acceleration times mass due to gravity.
So the Earth is pulling.
160 pounds.
Yeah, so the Earth is pulling you with a force of 160 pounds. Okay, and what Mr. Newton says is you're pulling Earth with an equal and opposite force. Okay. So this lady is pushing the wall with, let's say, a 50-pound force, and the wall pushes back with a force of 50 pounds, and that's why she accelerates in that direction. Okay. This happens when you walk as well. What do you have to do to walk? You have to push back on Earth, and you hope your foot doesn't slip, and the Earth pushes you forward, and the Earth is what propels you. Okay? So that's Newton's third law. So you rely on it all the time. Mass is just how much stuff there is in an object. The weight of the object is how hard this object is pulling it. So for instance, the astronaut's mass is the same here on Earth and on the moon, but his weight on the Earth is 6 times greater. Okay? The SI unit of mass is kilograms. Force, the superposition principle. So here's so this girl is applying a force on her, and she's applying a force on her. The net force is the sum of this force plus this force. That's the total force. Okay. Now the superposition principle states the following. If on this girl there are 2 forces acting like that, or one single force acting like this. From the motion, you can't tell if there's 1 force acting or 2 forces acting. Okay? So the effect is the same. And that's it. So when several forces act on a body, the effect is the same as that of a single resultant force. Okay. So let's say you can have 10 forces acting, 9 forces, 8 forces, or 1 force acting. As long as the net force is the same, you can't tell how many forces are acting. Okay. So here's the force acting on an object of mass 1 kg is 1 Newton when its acceleration is 1 meters per second squared. So here's an operational definition of 1 Newton. 1 kg is about 2.2 pounds, and when it's accelerating at 1 meters per second square, the force on it is 1 Newton. So the gravitational force, the Earth's gravitational force is the force with which it's attracting you. Okay, so if you were in the US, the force of gravity is pointing in that direction, and you go to Australia, the force of gravity is in that direction. Okay, the magnitude of this force is called your weight. Your weight is the same. Okay, the magnitude is the same. So what we're doing now is introducing various forces that you'll encounter in problems. So you'll hear about this thing called a normal force. Okay, let's look at this laptop. Earth is pulling the laptop down. Why isn't the laptop accelerating?
Your hand's applying the
Okay, so
exact same force.
okay, so if it's at rest, this force that your hand applies is equal to this force. Okay, and what happens is these atoms push on the atoms in your hands. The electron clouds deform a little, and that electrostatic repulsion, that's the force that's being applied. It's called a normal force because it's perpendicular to the two surfaces. Okay. So that's the normal force, and this can vary. How can this vary? So right now, the normal force on this thing is equal to the weight of this object. If I press down on it, so if the weight is 20 pounds, right now the normal force is 20 pounds. Now if I press down with 10-pound force, what is the normal force now?
30 pounds.
30 pounds. Okay, so you guys understand? The normal force can change. We'll do a lot of problems where objects are on an incline. Okay, so we want to make sure that we understand this. The force of gravity is vertically down. Okay, so this force, what's useful is, what we want to do is we want to break this down into a component perpendicular to the surface and a component parallel to the surface. Okay, those components are more useful. Okay? So let's make sure we understand that. And you pretty much have to commit it to memory. Okay, so the angle is defined by this angle theta. The slope is defined by this angle theta. Okay. So there is mg. Okay. Okay. What is this angle equal to?
90 minus theta.
Mm-hmm. Okay, and and then we'll complete this triangle. Yeah. And so this angle is theta. Yeah. So this is the right angle triangle. So this will be the hypotenuse. This is mg is the hypotenuse. Okay, so mg, and this is theta. So this is the opposite side, mg sine theta. And this is the adjacent side, which is mg cosine theta. Okay, so if this is mg, this component is mg cosine theta, and this component is mg sine theta. Okay. So again, now let me draw a clean diagram. So on an incline theta, there's the force mg, and what we want is this component, which is mg sine theta and mg cosine theta. All right, so you'll be using that quite a bit. Okay, and so that's the component of the weight of the guy on the slope, and so the slope is pushing him back. If he's not coming off the slope, that normal force is equal to mg cosine theta. Okay. Now, here's a trick to make sure that you understand it correctly. How do we check this? Okay, what if this theta is 90 degrees? So what if the slope is like that? What is the component of the force parallel to the slope? It's like free falling. It should be mg. And sine 90 is 1, so the force will be mg. If theta is 0, okay, so what is the force along the horizontal, along the slope?
0.
Right. So this would be mg, and the force along that line, along that, would be 0. Okay. All right. So again, you just have to remember this. Okay. So here's another thing. There's theta. The acceleration due to gravity is g, and this would be, the acceleration would be g sine theta. Okay, so this acceleration along the incline is g sine theta. And in fact, we'll use that in lab today. Okay. So we'll use that today. Okay, you have to understand this term tension. Okay, so the best way to remember this is take a rubber band, and let's say I pull the rubber band. If I'm going to hold on to the rubber band with my left hand, and I'm going to pull it with 10-pound force. Okay, so here's one end of the rubber band, and I'm pulling it with a force of 10 pounds. So the tension in the rubber band is 10 pounds. Okay, so my hand is at rest on the right. I'm pulling with 10 pounds, so the rubber band is pulling me back with a force of 10 pounds. What is the rubber band doing to this hand?
It's pulling with 10-pound force.
In this direction. What is the rubber band trying to do? It's trying to become smaller. So whatever is attached to the rubber band, it's pulling it with that force. Okay, that's what tension means. Okay, so and we'll talk about tensions in strings and ropes. Okay, so if a ring is under a tension of 100 pounds, what that means is the string is pulling this object with a force of 100 pounds in this direction. It's pulling this object with a force of 100 pounds in that direction. Okay, so that's what the tension means. And there might be other forces on the object. For instance, here is the force of gravity. Okay, and so on. On this object, there's a force, the normal force, and then you'll eventually learn about friction forces as well. Okay. All right, so let's learn about springs first, and then we'll come to the fun stuff. Okay. You'll deal with springs. If you're an engineer, you'll deal with springs all your life. Okay. So here is a mass attached to a spring. Okay. So if you pull this object, so this is the unstretched position of the spring. If you pull the mass to the right, okay, so you applied a force and pulled it to the right. What is the spring doing?
Extending,
I'm sorry?
extending,
Yeah, what is it trying to do to the mass?
pulling back.
Pulling back. Okay. So this is the equilibrium position. If you disturb the object to the right, the spring pulls back. The spring force is in this direction. It's trying to bring it back to the equilibrium position. If you compress the spring, if you push it in this direction, the spring is trying to push you back there. Okay? So the spring force is what is called a restoring force. It's trying to restore it to your equilibrium position. For instance, here's a counterexample. Here's a marble on top of a hill. You disturb it, what will gravity do? It'll just make the ball roll away. If you roll it in this direction, gravity is just, it's not restoring in this case. Okay? But in a valley, if you disturb it, then gravity will be a restoring force. Okay? All right, so a spring force is a restoring force. Well, what is the magnitude of this force? It depends on how much you stretch the spring. Okay, so the magnitude of this spring force is kx. The negative sign tells you if x is positive, then the force is in the negative direction. If x is negative, then the force is in the positive direction. Okay, so the spring force is given by minus kx. What is this fella, K?
The spring constant.
He is the spring constant. What do you think that means? What does a large K mean? So if, I'm sorry?
It's the force per distance
Yep,
that spring applies.
so if you stretch the spring a meter, that would be the force. So the spring constant, it tells you how stiff the spring is. Okay. Stiffer the spring, greater the force it applies. Okay. So your car, for instance, has springs that have spring constants of 25,000 newtons per meter. Okay. So if you stretch, you can't stretch that spring a meter, but if you did, it's in the suspension, 25,000 newtons. Your weight is about 500 newtons. Okay. So it can lift 50 of you. And then when it stretches 1 meter. Okay. All right, so this is the spring constant, and it tells you how stiff the spring is. All right, again, it's a restoring force. You disturb this from its equilibrium position, and it'll try and bring you back to the equilibrium position. Okay. All right, so now let's do some of the fun stuff. Okay. So here's a suspension bridge. What is the idea of a suspension bridge?
Support the bridge from above instead of below.
Yeah, so okay, so here's an old style bridge. Okay, See, this uses a lot of material. It's not very high, okay, and so on. And so a suspension bridge uses a lot less material. It's very high, it can let ships go under and stuff like that, and you can build it across large waterways. Okay. Well, how does it do this? Okay, so in a later chapter you'll learn. All right. So let me ask you a question, and then I'll tell you the answer. Okay. So let's say these are concrete pillars, identical pillars, and what I'll do is I'll apply 1,000-pound force like that. I'm just making up numbers. Okay. So in this force, I'm applying forces to compress the pillar. In this diagram, I'm applying tensile forces. It's identical pillars. When is it more likely to break? Or are they equally likely to break?
Tensile, because trying to pull it apart.
Yeah, so most materials are much stronger under compressive forces. Under tensile forces, they're weaker, okay? So in fact, concrete is about 10 times stronger than tensile is under compressive forces. Okay, so this fact is utilized in structures like this. Whenever you want to apply large forces, that better be compressive forces. And smaller forces can be tensile forces. Okay. So let's say you got to lift this bridge up, okay, and let's say this is 1,000,000 pounds. Okay, so you want to apply an upward force of 1,000,000 pounds. What do? Let's say you put in 1,000 of these cables. Each cable is supplying 1,000 pounds. Okay. All right, so each cable is under a tension of 1,000 pounds. So let's look at a cable. Here's the cable. The cable was under a tension of 1,000 pounds, meaning the bridge, 1,000 pound of the bridge is being supported. So here's 1,000 pound, and then this cable is pulling it with a force of 1,000 pounds. So this cable, each cable is being pulled with a force, stretched with a force of 1,000 pounds. That's a small force, it can bear it. What is this cable doing? It's pulling down on this cable, and there's a net force on these cables. All those cables they're pulling down on this cable. Okay? All those cables are pulling down, which translates to this net force. And what happens there? These guys are pushing down on this structure. These forces add up to, the compressive force adds up to 500,000 pounds. Okay, so with this design, what you ended up doing is you made a bridge that crossed a large body of water. It was high, you used less material, and then in addition, the smaller forces were borne by thin cables, and the large force was borne by these guys. Okay? So all that stuff goes into that bridge. And where did you start? When you first realized that structures are stronger under compressive forces than tensile forces. Okay? All right, so here is what is this guy? So it's a machine. What does a machine let you do? I'm sorry? Yeah, so it lets you apply smaller input forces and get a larger output force. Okay? Sometimes you might apply a larger force for a smaller input force. Okay, so this rope is under tension, and the question is how much tension is in the rope. Okay, so if this is a 100-pound object, the tension is 50 pounds. Okay, and so you're applying a 50-pound force. You pull down with a force of 50 pounds, and you're lifting a 100-pound object. Sounds like free lunch to me. What gives?
You have to pull it twice as far.
That's right. Okay, so you will learn work is force times distance, and input work, assuming there's no friction, is equal to output. So to lift it 1 feet, you have to pull down 2 feet. Okay. The mechanical advantage of this is machines have mechanical advantage is the output force divided by the input force. So in this case, 100 pounds is what you lifted with an input force of 50 pounds. So the mechanical advantage is 2. Okay? So you multiply the force by a factor of 2. This guy, okay, so this tension, okay, and again, this has a mechanical advantage of 2 as well. Okay. So all you do is count the number of strings pointing up, and you can lift a 100-pound object with the 50-pound force. Okay. Same thing here. On this guy, with this pulley system, you see this tension is lifting it up, this tension is lifting up, this. You can lift a 100-pound object with a force of 33 pounds. Okay? So this guy has a mechanical advantage of 3. So to lift this object 1 feet, you have to pull down on the string 3 feet. This guy, there are how many strings going up? 1, 2, 3, 4. This guy has a mechanical advantage of 4. So you can lift a 100-pound object with a force of 25 pounds. Yeah. Looks like you can keep going. Yeah. What gives here? The more moving parts you have, the greater the friction, and then maybe the advantage won't be as great. Okay? So, all right. So we know about springs. Here's an interesting object. Okay. Which way will this move? Will this fall down, or these guys fall down?
It depends.
It depends. Okay. So if M1 is greater than M2 plus M3, then M1 will fall down. Okay? If M2 plus M3 is greater than M1, then M1 will go up. Okay? So here's a very interesting device you can make. Okay, again, if M2 plus M3 is greater than M1, you'll have M1 going up. So here's M1, M2, M3, M4. So if you put sand on these buckets and those guys are heavier than this, then you don't need any nails and this thing won't fall down. In fact, you can make the weight of these guys greater than this bench plus your weight, and you can sit down and it won't fall down. Okay. right, one last idea and then we'll be done with this chapter. We want to understand this idea of non-inertial frames. Okay, we learned Newton's 3 laws. What does the first law say?
Velocity is
There's no
constant.
force on an object, its velocity is constant.
Oh, very good. So first law is if the force is 0, then A is 0, V is constant. Okay. Second law says if the net force is not 0, then you're accelerating. And what does the third law say? When two objects, yeah, when forces always come in pair, when two objects interact, the force one exerts on the other has equal magnitude, but they're in opposite direction. Yeah. Now, these Newton's laws hold in what is called an inertial frame of reference. An inertial frame of reference is a frame of reference that is not accelerating.
So it still applies if it's just moving at a constant velocity?
Very good, my friend, very good. Okay, it should not be accelerating. Okay, so let me give you a counterexample. Okay, all right. So here's we're going to play ice hockey. Okay, so we're at the North Pole and Santa Claus hits a puck. Now he hits it very hard. Okay, so let's say if you're in a geostationary satellite, okay, what you see is the puck's traveling straight. Let me be more careful. Yeah, okay, geostationary. No. Geostationary is the same as fixed. Okay, so if you're hovering over the Earth, you see the puck traveling straight. But if you're standing on the Earth, what happens? The Earth rotates, and the puck seems to go in that direction. Because the Earth spun under the puck, and the puck went in that direction. When you're standing on the Earth, you're in a rotating, the Earth is rotating, it's accelerating, you're in a non-inertial frame, and an object deflected even though there was no force acting on it, which is not what Newton's law says, first law says. So these guys are not valid in non-inertial frames of references. Okay. So for instance, let's say, so here's a classic example. You're driving on a car and you hit a curve. If you're curving to the left, you feel like you're moving to the right. You feel like there's a force acting that's pushing you to the right, but there's no force acting on you. In a non-inertial frame of reference, you feel this fictitious force. Yeah. You are actually going straight, but in that frame of reference, you appear to be going to the right. Yeah. So Newton's laws are only valid in inertial frames of references. Okay, those are frames of references that are not accelerating. Okay, so they can be moving at constant velocity, but as long as you're not accelerating, then Newton's laws are valid.
What does that say?
V is constant.
Oh.
Yeah. Okay. All right. So that